Unit 5, Part 2. So I'm going to do exercise 1B from page 92, from the back of Unit 5, and show you how to perform a truth table test for the validity of an argument form. But as I do so, I will explain theoretically how truth tables make it possible for us to actually, now for the first time, prove that an argument form is valid if it's valid, or see it, how they allow us to do that. Okay, so get the problem in view. Okay, this is a particular argument form, right? An argument form which is a set of statement forms. This one has two premises and a conclusion, right? So if I'm given as true, right, remember validity is if the premises an argument is valid when it's the case that if the premises are true, it's necessarily the case that the conclusion is also true, right? The inference from the premises to the conclusion has to be truth preserving. We're talking about truth preserving in Unit 6. But that's a valid argument, right? You can't possibly go, a valid argument is one where it's not possible for the premises to be true and the conclusion false. If you're given true starting points or premises, your conclusion will also be true. You preserve truth as you move to conclusion. Okay, so this is a particular argument form. What does it say? It says, just reading the symbols, if I'm given if P then Q, and also given not P, question, am I entitled to infer not Q? Right? Can I infer with certainty that if P and Q and not P are true, then not Q is true? Also learn to be able to say it like this, because the next way I say it will be respecting the fact that P and Q are sentential variables, which can take as substitution instances any sentences, simple or complex, and no matter how complex, right? So say it like this and be able to see and read it like this. The question, otherwise put, is if I'm given any conditional, right? If I'm given a conditional, where the A is just completely general, given any conditional at all, right? So any formula where the major operator is a conditional, that is a conditional. What the major operator of a formula is, that is what it is that the formula is, right? The major operator is a conditional, that is a conditional. Okay. If I'm given a conditional, and I'm also given the negation of the antecedent, am I entitled to infer the negation of the consequent? Right? If you say it like that and understand it like that, you'll be able to, you're hearing it in its full generality, right? Such that you'll be able to recognize in a particular example, like, I don't know, A by conditional B, and Q hook E by conditional F, right? Right? If you hear it the way I said it there, given any conditional and given the negation of the antecedent, am I entitled to infer the negation of the consequent? Right? You hear it like that, you should then be on the way to seeing in something like this, oh, look, this is a substitution instance. These two formulas are substitution instances of the two premises of this argument form, right? Because this is a conditional, and this is the negation of the antecedent of the conditional. You see that, right? Because what's the major operator here? Big, long, ugly thing, but the major, hook, this other thing, right? But nonetheless, it's clear, pair the brackets, pair the parentheses up, you'll see, this is a conditional, that's the major operator, and this is indeed the negation of the antecedent of this. So here I am given a conditional and the negation of the antecedent. So it would behoove me to know whether I am entitled to infer the negation of the consequent. Right? Am I? Right? This is recognizing recognizing argument forms and statement forms in big, long, in big, ugly formulas like these. It's a big part of what we'll be doing in the second part of the course, especially on proofs. It's basically the bulk of what we'll be doing there, right? Because if this was a valid argument form, and this argument form constituted a rule, we'll see that it doesn't, because it will turn out it's not a valid argument form. We will find a counterexample. But if it was a valid argument form, then we'd be able to, if given this in a proof, in proofs we'll have a vertical line and we'll have a list of formulas. If it was a rule, like the ones on the inside cover of your book, those are all valid argument forms, those are all rules for inference, then we'd be able to go from these two and we'd be able to write down the negation of the concept. We had to write not brackets E biconditional F and cite the rule, and we would be preserving truth. We'd be going from things which are true to something else which is true, right? But the point of that was to get you to recognize the importance and be able to see in this form something like, this is a conditional. The question I'm asked, when asked after whether this argument form is or is not valid, is this. If I'm given a conditional and the negation of the antecedent, am I entitled to infer the negation of the consequent? Okay, now, look at the argument form. It's a set of statement forms. Okay, what is a statement form, right? You've got the sentential variables, P and Q, right? In this particular statement form, the first premise, you've got both P and Q, all right? And it's P and Q combined via a truth functional operator, right? And for every argument form we test, right, every argument form we can test in sentential logic, that is also true, right? Every argument form is sentential variables combined with truth functional sentential operators, right? It's either a hook or a dot or a tilde, right? as in here, right? Or a wedge or a triple bar. Those are all truth functional sentential operators, right? Which means, and that's true of every statement form making up an argument form, right? So that means everything, right? That means we have a truth functional system of logic. The only operators, the only connectors we work with are truth functional ones. So just focus on this statement form, the first one. The operator's truth functional. The only thing that goes into determining whether this statement form is true or false is the truth values of the sentential variables, right? It's a truth, the hook, like the tilde and like all our sentential operators, are truth functional sentential operators. The truth value of the compound built with them, so the formula, right? The truth value of the compound built with those operators is determined entirely merely by the truth value of the component sentences, right? Which in this case will be the P and the Q, right? The sentential variables, right? So think of what the truth table gives you. I have this particular argument form. It has an infinite number of substitution instances. Not only that, it has an infinite number of substitution instances for each row of this truth table, right? Just take row 1, right? Column, 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 columns are up, down, rows are across. This first row, right, that is this particular argument when P is true and Q is true, right? We're going to be calling this a substitution instance, but you've got to recognize this one substitution instance, right, this row in the truth table, nonetheless stands in for an infinite number of actual substitution instances when we're understanding substitution instances as particular arguments with particular meaningful English sentences, right? You can take two sentences which are both true, right? You can put them into this particular argument form. That's one substitution instance of this argument form where P and Q are true. Take another pair of true sentences, right? Different sentences where they're both true, that also fits into here. But here's the thing, right? Because it's here's the crucial point, because it's a truth functional system of logic, right? The actual content of those sentences doesn't matter, right? Since all of them are with P and Q both true, that fact, that P and Q are both true, is the only thing that matters for determining whether these sentences, the premises and conclusion, are true or false, right? And now, with that fact of truth functionality, we can bring the infinite number of substitution instances down to a finite number, because there's only a finite number of possible truth value combinations of the sentential variables. And what the base columns do in every case for a truth table is list all possible combinations exhaustively. If there's only two variables, like here, P and Q, it's just 4 rows. Q is true or false, P is true or false, Q can be, right, they can both be, Q can be true when P is true, Q can be false when P is true, or Q can be true when P is false, or Q can be false when P is false, right? If there were 3 variables, we would have 8 rows. I'm going to continue in the next part.